I'm gonna start the recording now. Okay, we're officially live. Welcome to Aerodynamics 101 Lunch and Learn event by Illinois Space Society. Woohoo! What is your name, sir?
Alex,
And what team are you in?
avionics, hardware.
Nice, welcome. We welcome all non-AE majors. This is what this Lunch and Learn was geared for. Hopefully I give you a brief taste into what aerodynamics is. It's stuff from AU 202 at 311 and 312, so it's three classes kind of compressed into an hour, so there's a lot of detail I'm missing out, but sorry. Hopefully I'm able to like hit the highlights. And give you information that's useful for space shot or other like aerospace projects within ISS. So here's the game plan. First, I'll talk about what aerodynamic forces are, where they come from. And one of those components is actually pressure, spoiler. And so I'll talk about pressure, how that varies within the atmosphere. And then I'll talk about the Bernoulli pressure equation, which describes different types of pressure that we're dealing with. One of them is called dynamic pressure. And this tends to affect drag and lift quite heavily. So I'm going to talk about drag and lift. But also, we like to express drag and lift as these coefficients, these non-dimensional coefficients called drag coefficients and lift coefficients. So why are aerodynamicists so obsessed with coefficients? I'm going to talk about that. And some of the more famous coefficients or non-dimensional quantities out there are Mach number and Reynolds number. Those are actually unitless as well. And speaking of Mach number, why not talk about supersonic flow? Those are high Mach flows. Those are exciting. It tends to get people interested and also relevant to some of the data that we saw and understanding the data that we saw in the space shuttle launch. That went supersonic, so we are able to see trends that I'm going to talk about, I think is pretty exciting. And then to show that data, we're going to introduce LabVIEW, which Anna and Dawson, what is it? Oh, sorry, FlightView. Not LabVIEw, sorry. That Anna and Dawson and so many smart people and you guys have been working on. So that is the game plan for today. So what is aerodynamics? It is a bit corny, but I start with a definition. Yeah, it's the study of properties of moving air, how air interacts with the structure that we flow over. I think so there's that. And so where do aerodynamic forces actually like come from? It comes from the fact that let me start drawing, let's say, because well, I'm an aerospace engineer, so I'm gonna choose an airfoil as the body, a solid body in this example. So let's say you have a solid body, like an airfoil here. As the air travels over it, as this thing moves through the air, it's gonna feel two types of forces. One is pressure, like as I mentioned already, and pressure is the force that will act, like if there's a surface here, it will act perpendicular to that surface. So this form of pressure includes the pressure that you feel like right now, because we're being weighed down by the atmosphere, and the other types of pressure that I'll talk about. So for aircraft to fly, for this airfoil to fly, which side has higher pressure, the top or the bottom? Yeah, the bottom. Yeah, the bottom has higher pressure in the top, and the net resultant force is going to point up. Yeah. So I talked about pressure, but the second type of force that this body will feel is called shear. Shear is the force that is parallel to the surface that you're feeling, kind of like if you're like rubbing your hands against each other. That's kind of like the shear force you're feeling. So as the air flows around this body, it will rub against the surface and introduce some shear forces. And that force as well contributes to the overall aerodynamic force that the body will feel. So pressure and shear are the main things. However, because our undergrad brains are limited and there's so much to teach in aerodynamics, in a lot of our modeling in 300 level aerodynamics courses, we kind of tend to ignore shear. We make this assumption called inviscid flow. Sorry, inviscid. Can't. Yeah, yes. Sorry, been a long day already. Inviscid flow And that's a type of flow where you assume the shear forces are negligible. It's just pressure acting on the system. And this is pretty valid for most analysis, but be careful, it's not always valid. So if people are spewing, if your aerospace friends are spewing out equations telling you, oh, this is the force, ask them, hey, what assumptions did you make? Did you make an implicit assumption? And if so, is that valid in our case? Always ask that. Always ask what assumption the aerodynamicist is making, because they make a gazillion assumptions. But yeah, like I said, we mostly focus on pressure. And so let's talk about pressure. I think you guys kind of have an intuition that yeah, pressure is pretty thick, pressure is pretty high, close to the ground, and gets lower and lower as you go higher to the atmosphere. And you can model that pretty well using this exponential model. And it holds up pretty well up to about like 100 kilometers, which is where the boundary of space is considered to be. So what exactly is the model? I guess the next slide will show it in detail as well, but I can draw it out here as well. So the pressure that you feel at a certain altitude will equal to the pressure at sea level times the exponent of your current altitude over something called the scale height. And by the way, this means raised to the power of e. So this whole expression means e to the power of negative your height divided by something called the scale height. And the scale height is roughly 8.5 kilometers. And the reason we define it this way is, well, here. Like I said, scale height is 8.5 kilometers, and this is kind of, this is not pressure, this is actually density, rho. And you can see that around where the scale height is, this website says 10 kilometers, I'm going to say 8.5. So at this point, your 1 over E ratio of whatever your sea level pressure is going to be. Like if you look at the equation here, yeah, if little h here is equal to big H, then this equation turns into rho equals rho naught. Rho naught is sea level density times E raised to the power of -1. And E raised to negative power of 1, that's roughly 37%. And I guess like in terms of mathematical models go, using E is clean, so that's why we like to model it this way. But yeah, kind of keep in mind that yeah, around 8.5 kilometers up in the atmosphere, we get 37% of what the sea level density is and what the sea level pressure will be. So okay, using that fact, kind of think about like what is the density going to be at like 85 kilometers? So that's kind of near the Kármán line, and that's kind of what we're hoping to shoot for. This is actually near the edge of the stratosphere. Well, okay, using this model, let's think about this. Okay, 85 kilometers, that's 10 scale heights. E raised to the power of -10, that's yeah, 0.0005. So 0.0005 of this value is the sea level density. That gives us the density at that edge of the stratosphere. Yeah, that's really, really small. You're not gonna, that's hardly any atmosphere out there. So yeah, just keeping this equation in mind, just very simple equation, just P equals P sea level exponential of your altitude divided by the scale height being 8.5 kilometers. That just enables you to just on the spot give you an answer. Okay, like space shot structure wants to know, what's the pressure going to be at 30 kilometers. Like instead of looking up U.S. atmosphere and going through all that Google search, just whip up your calculator, whip up your phone, and just plug this simple equation, and then you got a good estimate. I think that's really powerful. So this is how pressure varies as a function of altitude. But that's not the only way pressure varies. There's also, you probably saw the Bernoulli equation from one of your science classes. So there are 3 terms of like sources of where pressure can come from in a moving fluid. This website called it pressure energy. I'm going to call this static pressure. And this is kind of like the pressure that you would normally think of when you think pressure. Like if you have a moving fluid, and you have like, I don't know, a cylinder around it. I guess like what is like the pressure that the wall of the cylinder feels? I guess that is static pressure. You could think of it that way. And the second term, you can kind of think of it as representing the kinetic energy of the fluid, and we're gonna call this dynamic pressure. And this third term, we kind of tend to ignore as aerodynamicists. Sorry, if you're doing like hydrostatic, if you're a hydrodynamicist, maybe you would care about it more, but yeah, we don't care about this term. Sorry. But yeah, as I talked about already, we have different types of pressures: static pressure, dynamic pressure. Third term that is often neglected. And okay, so I can talk static pressure. It's like I said, it's the perpendicular force you feel. So what is dynamic pressure? What is dynamic pressure? It's denoted often as Q, and it is 1/2 the density of your fluid times whatever the velocity of that fluid is squared. And just for nomenclature, people sometimes use V for velocity. A lot of fluid dynamicists also use U for velocity. So if you see U, just know that, okay, they mean V, velocity for V. And we define this quantity called total pressure, which is an addition of the static pressure plus the dynamic pressure. We like to define that because it tells you a lot about the fluid that you're moving in. Like for instance, I don't know, if you let's say if you were to take the ratio between your static, this is your static, and your total pressure. Total is often denoted with the naught at the bottom. So if you see that also means total pressure. Now, if this ratio is like really small, what does that tell you about the fluid? That's just off the top of your head. I don't know. It's moving really fast. Yeah, because the dynamic pressure term is big. Yeah, exactly, exactly. Versus, yeah, if this term, oh yeah, can this term be bigger than one?
So.
Yeah, you can't, right? Yeah, because static is a term. Yeah, static can equal total pressure, but yeah, static can't be bigger than total pressure. Exactly. Exactly. So yeah, this ratio is always gonna be like equal to or less than one. And yeah, the size of this ratio. So like if you go to like wind tunnels and aerodynamicists take like total pressure readings and static pressure readings, that ratio will give often tells them like how fast is the fluid moving inside the tunnel itself. And this is actually how a device called pitot tube operates. It takes the ratio between those two pressures and when it enables you to spit out a velocity of your aircraft. So it's like, yeah, pitot tube. That's how it's spelled. So anyway, I guess I kind of explained this already, but to phrase it differently, like dynamic pressure is like pressure from speed. And you can kind of think of it as like the intuitive ways, like the pressure you feel because the air is flowing. You stick your hand out into an airflow and you feel pressure. That's dynamic pressure. I guess like the way like technical definition is this is the thermodynamic definition, like the pressure you get from isentropically converting the kinetic energy of the fluid into pressure. That is like the technical definition. But yeah, basically it's the same thing, I think. And I mentioned that dynamic pressure is often like denoted with the letter Q, and this is actually where the term max Q comes from. Like if you like watch like I don't know like SpaceX launches or just launches, people call out, oh, we're going through max Q. Yeah, this is when at the point of the rocket's launch where there's maximum dynamic pressure. Yeah, the rocket's accelerating, the speed is picking up, but as it's going up, the density is going down because it's going up higher up into the atmosphere. So at some point, the dynamic pressure will peak and then start to go down as the density goes down. And yeah, I already mentioned the equation for dynamic pressure. It's got three terms. It's one term, but like three factors in it. There's the 1/2 term, there's the density term, and there's the velocity squared term. Okay, and it's an important term in aerodynamic forces, as you will see why. So aerodynamic forces, we often think of split it up into two components, lift and drag. Anyone like want to like venture and give a definition for those two forces? And if you're a junior or above in aerospace, you can't answer, sorry.
Lift is the upward force on the aircraft.
Upper force, okay.
Yeah, and then drag is the force opposing the motion of aircraft. So it's a rocket, it should go down, it's a plane or whatever, it should go backwards.
Yeah. I think that is a good way to think about it. Yeah. So if you have a plane right here or a fighter jet, yeah, your thrust is gonna push it this way. Your drag is gonna push you backwards. Lift is gonna pull you up. Weight pulls you down. It's mostly right. Okay? Here's like a very like anal. If I'm going really being really anal, here is the exact definition. Lift is whatever force is perpendicular to the flow, and drag is whatever is in the direction of the flow. So yeah, let's say your wind is moving this way, and then yeah, going back to the plane example, your plane's flying this nice and dandy. Yeah, your lift is acting up because your flow is well perfectly parallel. So your definition holds, and same goes for the drag. It's pointing backwards because well, it's parallel to the flow here. What if your plane is or your rocket is turned a little? Then what? Then your lift still acts up, but your drag still acts parallel. So it's not necessarily the body that defines the frame, but the flow defines the frame. So yeah, I know it gets a little tricky. Like most of the time, like you like to think the flow is aligned to the body, but sometimes you do turns. Yeah. So there's that like slight correction, but it was a good definition. Thank you. So yeah, well, what is the magnitude of these forces? So the force of lift is equal to the dynamic pressure, which I said was 1/2 the rho times velocity squared, times something called a reference area. And for wings, for like aircraft, this is often the size of your wings. So wing size, so wing area, your top-down view of your wing. I don't know how this area. But also I've seen it like let's say like you're trying to calculate, I don't know, width of a very blunt, I don't know, like a missile or something. You can just choose the cross-sectional circular area as well. Like your reference area is like pretty much like whatever you define it to be. So again, when an aerodynamicist says, here's the reference area, ask them like, okay, what did you choose? Which convention did you go by? So anyway, going back, so you have the dynamic pressure, you got the reference area, and you multiply it by its coefficient. So coefficient of lift for lift, coefficient of drag for drag. The equations look almost identical, except for those different coefficients. And you can kind of see if you look at the equation that CL and CD are unitless, right? Because on the left hand side you have force, and dynamic pressure is pressure, and then you're multiplying it by area. So that already gives you the right units that you need. So CLCD should not have units in them. Yeah.
So
yes.
Sorry. So are the reference areas always defined like with respect to the body? That like they have to be, right? Not the flow. Like, because I was thinking, it makes sense that like, let's say we have the missile, right? And it shows the circular area. If the flow is like aligning the missile as you kind of would imagine it makes sense that like the drag reference area would be cross-sectional. But like, why is the lift reference area the same as the drag reference area? Or are they?
I feel like if you're like analyzing like the same body, you would typically choose the same reference area. So if you were analyzing a wing and trying to analyze the lift and drag for that, you would use the wing area for both reference areas. But I guess
yeah. Try to take work.
Yeah.
Okay, and then like I guess the coefficients things to count for that. The coefficients.
Exactly. And that's kind of like the point I wanted to make as well. If you look up like, I don't know, drag coefficient of a wing versus like of an airfoil versus like a flat plate or a prism, you'll see values and take those with a grain of salt because if you airfoil area is generally when they do CD analysis, they use area which is the area of the wing.
Okay.
But I feel like when they do, I don't know, like more blunt body analysis, they sometimes use, I don't know, cross-sectional area or even like the wetted area. Wetted area is kind of like the surface that would get that is wetted by the fluid that it's moving in. So like the total surface area. So there's like a lot of conventions out there, and you just gotta be like dig deep into your sources and ask, like, okay, which area did this person use to get those coefficients? You gotta be really careful. So that you're not comparing apples and oranges.
Right.
Yeah.
Okay. Thank you.
Yeah. Good question. Um, well, yeah, lift coefficient and drag coefficient, those are non-dimensional quantities, and they're yeah, if you arrange the equation from earlier, the equations, you can see that yeah, you get this ratio here, and they define the drag coefficient. And like I said just a few seconds ago, be careful, you know, that you know how exactly they defined S, because it will affect the value of your CO and CD. Like you have the exact same experimental setup, like you got the same lift and drag measurements, you use the same dynamic pressure, but if you use a different reference area, then you're gonna get different coefficients. Yeah. But yeah, CL and CD, those are not the only non-dimensional quantities that aerodynamicists love to use. Like I think most of us heard of Mach number at this point. Most people just know it as it's the velocity that you of an object divided by the speed of sound. Okay, great. Actually, it's kind of more than that. Because so let's say you have your velocity u, and the speed of sound is actually a thermodynamic quantity, and it has to do with something called a specific heat ratio of the air times the specific heat constant of the air and the temperature of the air. Those two are constants, just something you kind of have to know, memorize. So what I want to point your attention to is this term here, temperature. This is measured in Kelvin or Rankine, if you're whatever. Um, so speed of sound is a kind of like a measure of like the temperature of the air, and velocity, you can think of it as, well, kind of like an analog to the kinetic energy that the air has. And well, temperature, you can kind of think of it as the analog of the thermal energy the air has. So you can kind of think of Mach number in this interesting way. Like I was taking a like a hypersonics course last semester, and the professor said, well, Mach number, you can even think of it as like the ratio between like the kinetic energy of that air versus like the thermal energy that that flow has. So it's just more than a way that people want to. It's just more than just the simple ratio of velocity divided by the speed of sound. It's not that aerodynamicists want to brag, like, oh, we went like 5 times faster than the speed of sound. Whoa, we're so awesome. No, it's not like we want to brag. It actually has a meaning behind it, thermodynamic meaning behind it, which I can't really get into because it's too much. You're going to learn about it in 312 if you are in aerospace. Um, or I'll talk about like how you can do the same, most of the similar calculations that 312 students do. It's like a calculator online, brilliantly set up. I'll go over that. So anyway, it denotes a very important like aerodynamic quantity or aerothermodynamic quantity. That's what Mach number is. And then another thing is maybe this is less popular, but just as important or even more important in the aerodynamic world is something called the Reynolds number. This is also unitless, and it is the ratio between the inertial forces and the viscous forces in a fluid. Like if as a fluid is moving, it has momentum, so it has inertial force. Like if you were to try to like, I don't know, like make the force the flow to rotate, then it will resist that rotation. So kind of like quote unquote centrifugal force. You can kind of think of it as inertial force. Viscous force is kind of like how thick the fluid is, how resistant it is to like shearing, so or flowing past the surface, how like thick it is. You can think of it that way. So this is the formula for Reynolds number. You have the density of the fluid, flow speed, and something called a characteristic linear dimension. I'll explain that more. And the um, the viscosities on the bottom. So let's say you have like water and honey. What do you think will have high Reynolds number typically? Like honey's thicker. So what does that do to Reynolds number?
Well, the viscosity is higher,
Viscosity is higher.
honey, so it'll have a lower.
Yeah, exactly. Lower Reynolds number for honey. But okay, let's say you have just two streams of air and one is like way faster than the other. Now your velocity terms up here, speed goes up, Reynolds number goes up. Yeah. So when aerodynamicists like report their like wind tunnel findings, they will often use Reynolds number to like report like their x-axis will be Reynolds number instead of using wind speed. Yeah, I guess so. I guess you could kind of think of it as an analog to that. Oh, it's not a perfect analogy, but like higher Reynolds number means like higher speed flow. It also kind of means that your flow is moving past a larger object. Um, yeah, that kind of like goes over my head a little, but yeah, basically if you're like have flow, like exactly the same flow flowing over like a sperm whale, it's gonna have a higher Reynolds number than like say like flow moving over like I don't know, one of your like red blood cells or something. Because your red blood cells like really tiny.
Yeah.
Yeah. Um and Reynolds number, what it does is well I'll save that until the next slide. Hang on. So aerodynamicists love these dimensionless quantities. And why do you think that is?
So you just multiply different things by them to get information. I gotta have.
Yeah, I think you're getting to it. Yeah, it's kind of like distilled information. Yeah, you can just like multiply it back into your context and get your specific result back. You're right. Yeah, I think it allows for generalization of results. So for instance, if aerodynamicists results like publish results in velocity, and then well, let's say you want to replicate that experiment, then you got to ask that experimentalist, like, okay, what was your temperature? What was your density? What was your viscosity of the fluid at that day? You got to ask all these other questions because this doesn't contain enough information. It doesn't describe the flow fully. Um, so what some of these non-dimensional quantities like Reynolds number or Mach number does, it really distills like the essence of like the flow. This fact is really cool. If you have flows with the same Reynolds number, they will behave similarly. It doesn't matter if it's honey, water, air, CO2, or methane. If it has a similar Reynolds number, it will behave similarly. So yeah, if you just search Reynolds number, you'll see like flow structures like this. And notice that it's not fluid specific. As long as you have this range of Reynolds numbers, your fluid will likely behave this way around the circular object. I think this is really cool. So again, it really allows you to generalize results, kind of capture, like really characterize your like phenomenon with like one number instead of having to tag along, oh, velocity, viscosity, temperature, density, all that. No, just Reynolds number. And then same goes for the Mach number. I mentioned that it's an aerodynamic quantity, aerothermodynamic quantity, and it actually just knowing the Reynolds number and a couple of other things allows you to calculate like static to total pressure ratio, which I mentioned was important in figuring out airspeed and all that, and other important aerodynamic quantities. So yeah, you see like a lot of dimensionless quantities, and yeah, they're done for like easy communication between other aerodynamicists and allowing you to like generalize results. Um, and yeah, I kind of went over this already. If results were published in velocity, then yeah, you would have to ask all of these contextual questions. And then, yeah, going back to like the lift and drag example, like if aerodynamic forces were just published in pounds, like oh, let's say oh my wing got generated like 5 pounds of lift. Then you immediately ask, okay, what size wing did you use, and what was the dynamic pressure you used? But if you just publish, oh, my CD is this and this, and I used the wing area as my reference area. And boom, that's enough information for everyone to know. Like, okay, that's what you need. Okay, now let's speed up a little. Pun intended here, sorry. Supersonic flow. What do you guys first think when you hear supersonic flow? Any first impressions? This is open to everyone, not just our non-AE people. Pretty fast, yes. Need for speed.
You break the sound barrier, so there's wow.
I'm gonna talk about that cloud. I got some bones to pick with that. Okay, but yes, cool clouds, okay. Yes. Yes, extremely compressible flows, yes. Yeah, so I guess I can talk about hypersonic a little as well if there's time, but yeah, flow is very compressible. Oh yeah, this thought this was kind of funny. So aerospace engineers would generally associate below 0.3 Mach as being incompressible flow. So if your volume of air is moving at this speed or below, then yeah, your compression effects are like less than 5%. So you can pretty much assume that your density won't change. So like if you have this block of air moving here, then yeah, the density won't change. Yeah. Anyway, sorry, I thought that was kind of like funny because one of my I kind of like was in the CFD class for like couple of weeks, and I dropped out. But what the professor mentioned, how like we're kind of like aerodynamicists are kind of like Pavlov's dogs, kind of like you ring a bell and the dogs start drooling. Like we aerodynamicists, we see Mach 0.3 and we think incompressible. That's the immediate association we make, and I think I've become one of those people. So anyway, that's compressible flow versus incompressible flow. So yeah, if you see supersonic flow, you imagine stuff like this. You know, the Concorde. Hopefully we get supersonic flight back, or maybe it's back to the environment. Okay, so you got the Concorde, and then you got these images called Shear images. And what this does is actually allows you to visualize density change, which is super cool. Like as the density of your fluid changes, light refracts through it differently. So all this it allows you to see these lines, which represents the fluid structure that forms now supersonic flow. So I'm going to talk about that. And there are those clouds that people usually think are breaking the sound barrier, but it actually isn't. And I'll get into it by. Oh, what's going on? Yes. Okay, so supersonic flow structure. So this aircraft or model aircraft is in supersonic flow right now. Mach number is greater than 1. And what you see you do see a shock wave, yes. Because like, let's say something is moving through the air subsonically, then the air can kind of like get out of its way because the information that your hand is coming travels forward at the speed of sound, and it alerts the air in front of you that, hey, the hand's coming, move out of the way. But in a supersonic flow, you can't do that. So all those compression waves get compressed into a really, really thin layer. We have multiple compression waves compound to one really thin layer. You can see this layer right here. And that is called a shock wave. And there are kind of two types. One is called a normal shock, where the shock is perpendicular, 90 degrees to the flow. And this type of shock you see is called an oblique shock. And that's where the flow is kind of slanted against. The shock wave is slanted against the flow. So yeah, oblique shock waves, multiple compression waves compound into really thin, discrete, like really thin layer. And what happens when gas is compressed? Just going back to your physics classes. If you compress gas, what happens? It's not a trick question.
Well, I mean, there's PD and NRT, right?
Yes.
The volume has to decrease. Or the temperature has to.
Yeah, I mean, yeah, if you just think of it like you have a piston and you're just like pushing down on it.
Yeah.
You know, if you compress it, pressure spikes up, temperature goes up, and your density goes up.
Yeah.
And that's what happens as you cross the shock wave. And surprisingly, the flow actually turns, well, hang on a sec, this is not entirely accurate. The component of the flow, so let's say your flow is flowing this way, and you kind of split it up into a component that's normal and component that's tangential. The component of the flow that crosses the shock wave is always subsonic. Yeah. So shock wave will turn a supersonic flow into a subsonic flow. The normal component, that is, will turn subsonic. And actually, shock waves are invisible. Ooh, what are those vapor cones that I see then? Yeah, so you have to do something like this, the Shear imaging, in order for you to see supersonic flow structures. And if you take A312, you learn about all this. This is flow past the wedge, yeah, oblique shockwave stuff. Okay, I don't think many of you have heard what expansion waves are. Well, I didn't. I certainly didn't until I took 312. It's actually formed when the fluid is forced to expand. So let's say you have, I don't know, like a ramp here, and you're a very fast flow moving, and you would like to just go this way, but no, you gotta fill up this volume as well. So fluid turns, and your volume of air expands. It's forced to expand. What happens if a gas expands? It's the opposite of compression. Your density, temperature, and pressure all gets lower. And actually, you speed up because, well, I don't think it's, well, yeah, you actually speed up. So you can get subsonic flow and turn that supersonic. So yeah, expansion waves are kind of like the polar opposite of shock wave. You can think of it that way. And here you see a diamond airfoil and what kind of shock structure would see. So in the leading edge, the edge that sees the flow first, you get oblique shocks that, what does it do? It compresses the flow, makes it hotter, makes it denser, and slows it down. But as you turn this edge, the fluid is forced to expand. So what does it do? It cools down, the pressure drops, density drops, and it speeds up. And then, well, you get the final shock. But yeah, so oblique shock and expansion waves are kind of like coupled together because, yeah, you're like, I mean, your geometry of your spacecraft of your aircraft will always be that you're hitting the flow at one end, and then you're kind of like tapering down, so you're going to force the fluid to expand somewhere. And kind of this is what you see in these other more Schwerin images. This is a bow shock, a type of shock wave. And then here, what you see here, that I think those are expansion waves. Like the air is forced to expand here. Yeah, it forms to span these spans, which are expansion waves. And these are the equations that govern that flow. Okay. And going back to the vapor cone example. Yeah, so this is water vapor in the air dropping out because the pressure is dropping because the temperature is dropping. What drops temperature and pressure? Is it compression shock waves or is it expansion waves?
Expansion.
Yes, expansion waves. So what you see here is not a shock wave for crying out loud. These are expansion waves that you see, and those can actually happen even when you're not supersonic. These are shock waves. So please don't be one of those people who post on social media saying like, "Oh, shockwave's cool, blah 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 blah," and choose to put these kind of images as your caption. Please don't do that. It drives us crazy.
It also makes sense that it's not shockwaves aren't happening at the front.
Exactly. Yeah, shockwaves will be happening here.
Yeah.
What here is kind of like I guess like what's happening here is that like you have this kind of looks like a duck. Yeah, your flow is expanding kind of like here, well, versus it will be compressing here. So yeah, it doesn't make sense. This would be where the shockwave would occur. Yeah. So Yeah, this is, I showed you this equation, I showed you this equation, and it's not to just like tease and be like, haha, we get to learn this while you don't. No, that's not my intention. I'm saying that this source here called Virginia Tech Compressible Calculator will actually solve the same equations I showed you. So if you have your laptop, it's time to pull it out because I got an example question for y'all. Right. So search Virginia Tech Compressible Flow Calculator. When you open up the page, it looks like this. And let me give you an example problem that kind of hopefully you are able to solve now because you are aerodynamicist or aerodynamicist adjacent or adjacent. I feel like I am aerodynamicist adjacent, and so that makes you adjacent to adjacent. Anyway, so you have a wedge of 10 degrees. So this 10 degrees here, and this is the wedge angle. Lying at Mach equals 3 at an altitude of 8.5 kilometers. Oh, that's the scale height, right? And then now tell me, what is the pressure behind the shock that forms?
So this is a weak shock, right?
This is a weak shock, yes. So I guess like for step one, so if you look at the calculator, if you go back to the calculator, you'll be using the oblique shock section here. The default value of gamma is correct. That's the gamma for air. The input 1. Mach 1, M1, that is 3 here. And then the turn angle is 10 degrees. And it's turn angle weak shock. It's weak shock. And you should be able to get the P2 over P1 ratio. That's the pressure behind versus pressure before the wave. You should be able to get this value. What did you get? 2.05. Gotcha. Okay, I think that sounds about right. Okay, now what is pressure before the shock? We got to know that too. Ooh. What now? Yep.
Just the pressure before the shock, not in relation to anything else, or
yeah. So this just gives you the pressure ratio.
Right.
Right. But in order to get the pressure behind, you got to multiply this by P1. So what is P1?
Isn't it just because we're going in Mach 3, the information that we're coming is like traveling ahead of us. So wouldn't it just be the static pressure of
Yes. So P1 is the static pressure of the fluid before it hits the shock wave.
Right.
So that's the pressure at height of 8.5 kilometers, which is gonna be
right.
1 over E. Yeah, exactly. The pressure at sea level. Yes. Do you know the pressure at sea level off the top of your head? Okay, I'm gonna approximate. It's around 100 kilopascal. Wait, right? Right? Perfect. Well, that's roughly right? 101. Yeah, let's be exact here. Yeah, 101, 3.5. 101.325? Yeah, 101.325 kilopascal. Okay. Wow. Yeah. So, okay. Yeah, you could use the standard atmosphere. You could also use the exponential model. Let's see, what's the use the exponential model. Let's see what's the pressure at 8.5. Yes. Yeah.
It's about 100.
Yeah.
That's nice. So you don't even need really a calculator.
Exactly. Yeah. And what did you get from the standard atmosphere? Is this pretty similar?
33.1.
33.1, and what'd you say again?
37. So.
Okay, so close enough. It'll be good for back to the napkin math. And yeah, times that by roughly 2, and yeah, there you go. You have your answer. So yes, so this is all just math and theory, but we want to see real data. Where's the real data? All right, here's where point here comes in. Thanks so much for standing by, Anna. Take it away. Okay. Okay. I will share. Wait. Multiple participant can share, and I'll stop sharing. All right. I believe we're still recording. Oh, I can just use that. Yeah, okay. I think I'll turn off this mic where I'll stop talking. There you go. Y'all can.
Okay, yeah, so that was really interesting. And what's even more interesting is to see all of that theory reflected in some of the real world data that we collect. Because every launch, we have an avionics bay on the rocket. And if you didn't know the role of that, one of the main roles is data acquisition. So you have lots of very high quality sensors. These sensors go on like industrial devices. And we use the same ones on our rocket. So here, it's something that some people on the software team hacked up in like a week, I think. So this is a very early stage of it. But the point is that you can see all the data in a very interactive way. I think the most relevant thing is the barometer altitude data, which we calculate by looking at air pressure and then, multiplying it by some constant and adding a little bit. But yeah, if we can look at barometer altitude, talk a little bit about that. And then for the range, just make it like the whole thing in the beginning. Yeah, okay. So if you look at the bottom, you can see sort of the whole flight, and that's supposed to be what the altitude was. And it looks like it makes sense, right? It goes up, and then there's a bit of a disturbance, which I'll talk about later, and then since we have a parachute, it kind of descends at a constant velocity. That's all fine. But what we're interested in is like why is there a giant dip? One giant dip, and if you go a little bit to the right, there's like a little smaller dip. That's because our rocket this time, and also in New Mexico and up, went faster than the speed of sound. And when that happens, the fact that we use a barometric altitude means that there's such a big spike in the dynamic pressure, as Sanyan has explained, that the perceived altitude that we calculate goes down because the pressure goes so high. And then when we leave that, we have a secondary dip that is smaller, but it's still there. I don't know, Sanyan can talk a little bit more theoretically about why that happens, and I can continue. But yeah.
Yeah, sure. I think what we suspect happened was that I mentioned that how pressure increases behind a shock wave. We think that as the dip was happening, um, basically the shock wave formed and our pressure sensors were behind the shock wave. So what it saw was the pressure suddenly like very increased a lot, and in our calculations that corresponded to a drop in altitude because since we're correlating altitude change, barometric pressure change with altitude change. So our rocket did not actually drop down to the ground almost. No, that's not what happened. Yeah, the pressure just spiked up because of the transition to supersonic flight that happened. And yeah, I think that accounts for the pressure, the altitude quote unquote dips that we see.
Well, another plot to see with this would have been the altitude. I don't know if altitude is, what am I saying? Velocity. I don't know velocity is one of the options on the checkboxes. State estimation. Oh yeah, state estimation. Yeah. Yeah, state. And if you could, and if you could do it with barometer, but you should be able to see that the place where velocity, I just want to see the correlation between velocity and that spectrum. Would be interesting. Do the barometer also.
Oh.
well, I was actually thinking that this would happen when we reach maximum altitude, but it seems like it happens in a different place. So, do you have any ideas as to why that?
I don't know. I don't know enough about sensors to answer that accurately, but hey, I mean, close correlation between like when we're hitting like our maximum speed and when the pressure dip is happening. Sorry, a pressure spike is happening. But yeah, I'll have to know more about sensors to answer your question. Sorry.
It seems like we don't have all the answers.
Yeah.
So that means,
It looks like a lot like his velocity being calculated off of pressure as well.
Oh yeah, that
Like,
yeah.
I think that's
that probably is it, isn't it?
right.
Yeah, so the way we actually get
Yeah.
velocity is like obviously, there's no substance, like they just have it's the one thing that would be impossible.
Well, we could use a pitot tube, but we didn't have a pitot tube.
Even if not also based on
That's based on pressure.
That's what. Yeah, there's a way to get around it, but we didn't have that device.
basically we have a team that with the GNC team. That's what they're trying to get around. They're trying to make something called a Kalman filter that takes in lots of different sensor data and then like comes up with this is what I think is the reading with the highest probability. So it was a mix of accelerometer and barometer, but it did rely on barometer to some extent, which is probably why it did get messed up at the exact same point, which is interesting. But
So it's not affected as heavily as the barometer reading itself, right? Because it's taken multiple factors.
Yeah.
But the barometer affects it, which is why like it starts to float down when you see the giant drop in pressure. It
Yeah.
doesn't plummet the same way.
yes, in fact, we can see a different because we also use a Kalman filter to calculate altitude itself, and we can plot barometer altitude along with state SX, which is position. Given state SX. Yeah.
Thank you guys.
And if you go to where the data happens, yeah, so the orange line is the altitude as calculated by the Kalman, which also uses accelerometer. You can see that it does like pretty well. Like it does kind of dip over there, but it's obviously not nearly as pronounced as the one barometer. So that's something they call it filter, I guess. Yeah, that's pretty cool.
Okay.
I think that's pretty good for us, unless there's something.
Right. Yeah. Shout out to Gautam and Anna and the Aerodynamics software team for working on this amazing tool. And it's gonna like come out in its full glory soon, right? And within the next week or so, yeah. It will be available on our website. On our website. Yeah, that's what we're shooting for. Sweet. Okay. Any last questions? Otherwise, I'm gonna end this luncheon run. Okay, no questions. I will end. Thanks so much for attending, everyone. Bye.